Hi, I'm Paul Nelson, and I'm an assistant professor at the University of Copenhagen. And this is a recorded version of the talk I'll be giving tomorrow at V2 Security called Confidentiality Beyond Encryption, Formalizing Metadata Privacy. So I want to start off and give us an example domain to make the problem a little bit less abstract. So I'm going to talk about instant messaging specifically, and a lot of you might be using instant messaging, for example, WhatsApp, Telegram, or Signal. So WhatsApp is pretty popular, has about 3.3 billion users per month. Telegram is also a big player, around 700 or so million users per month. And Signal, maybe less known, but very much profiled for being a privacy first focused kind of app. It has about 70 million to 100 million users per month. So different sizes of apps, but all instant messaging, right? And if you're using one of these apps, it typically has message confidentiality via encryption. And I don't mean just encryption, like TLS encryption between client and server, but a lot of the time you will also have an end-to-end encryption. So this is actually true by default in Signal and WhatsApp. In Telegram, it's not end-to-end encrypted unless you explicitly turn it on in a secret chat, but they have the functionality. But what this means, right, when we have message confidentiality for encryption, is that when Alice and Bob wants to chat to each other, they can encrypt their message and make sure that malicious Mallory over here, cannot read the message, right? So this is something that we want and something that we like, right? But I promised something about going beyond encryption in this talk. So here you might just think, well, it's encrypted, so what could go wrong at that point, right? Aren't we done, right? But let's talk about metadata because, what could go wrong? Famous last words. So let's dive further into the problem of this talk. So we have again Alice and Bob, and they're using instant messaging, right? So in most of these applications, that means that you have a centralized server. Some of them are distributed, but the most popular ones, for example, the ones that I showed, WhatsApp, Telegram, and Signal, there's a centralized server that forwards the messages. Now we see Alice and Bob a little bit more worried here, right? Because I will be introducing some problem. So when Alice wants to send a message to Bob, it gets first sent through the server where it's forwarded to Bob. And if we have malicious Mallory, again, actually able to observe the network, even if she can't read what's inside of the message, she can actually see that, Alice and Bob are talking. And you might say, well, the content is encrypted, how bad could it be? But imagine that Alice is actually a whistleblower and Bob's a journalist. So Bob actually takes the content of the message where Alice says, there is a really bad thing happening at my company. And Bob takes that content and publishes it in a public newspaper. So at the end of the day, one can find out through reading the paper that there must have been a whistleblower at this company. And if Mallory is able to observe the network and see that actually no one else from the company was talking to Bob except Alice, just the fact of communication at this point could be incriminating and put Alice in trouble, even though Mallory couldn't break the encryption of the message. So this is learned through transport layer metadata, and what you can actually find out is stuff like who talks to whom, when do these conversations happen, how often do people communicate, and so on and so forth. And from this you can learn about user behavior. You could learn who someone's friends is, maybe how close their relationship are based on how much they talk, and you can see when they are online and talking, right, and when they're doing something else. So this transport layer metadata actually allows you to learn a lot. Okay, but then you might say, well, didn't you tell me that WhatsApp has the number of billions of users and all of these services, it was at least million scale, right? How's Mallory going to find out who I am talking to? Well, happy you asked. There's this thing called traffic analysis, which sort of puts Mallory into being a strong attacker, because with traffic analysis, she can just automate this analysis of finding who is talking to whom and what's going on. There are now some systematization of knowledge over these traffic analysis papers, and in recent years there's over 100 papers talking about using machine learning to do traffic analysis on encrypted traffic. So it's not just plain text traffic, but encrypted traffic, and then conducting traffic analysis using machine learning is actually successful. So with the advances in AI, this threat is actually growing bigger and becoming more feasible. So that's scary. So let's look again a bit more at who is Mallory, what can she do, what do we mean strong attacker, right? I painted this muscle on her to show strong. What do I mean? Well, I mean a global external attacker. And by global, I mean that she can see the entire network. This is not necessarily because Mallory on her own can see everything, but she might be colluding with other network nodes so that they can get the full picture together. And by external, I mean that she cannot hack individual devices. Like she doesn't have access to what's going on the server, for example, or any user device. So she's still external, she's just looking at the network. And who could this be? Well, it could be a state or government. It could be an internet service provider. It could be an organization, someone with access to a lot of the network, or colluding parties. And she observes all the endpoints. So she sees Alice's device, she sees Bob's device. And her goal is to do what's called flow correlation. And this is actually the strongest attacker in this traffic analysis problem. So she wants to find out everything about who is talking and where is all the traffic going. Yeah, so it's a really strong attacker. A weaker one would be someone, for example, trying to do just website fingerprinting, where you're trying to find out what website someone is visiting, and then you only need a local attacker. Here that views some part of the network. So this is the strongest attacker, where you try to do flow correlation. We actually learned the most. Okay, so now you might be watching this in the context of V2 security, and then you might already think that, oh, this is problematic, I need no more motivation. But I'm also going to throw in the slide in case you're thinking, well, I've got nothing to hide. Why could this be bad for me? So I want to add some motivation here. So what if we have a government employee who's maybe a whistleblower communicating with a journalist, like the case I said before? And you might say, well, that's not really so relatable to me because I'm not a whistleblower, right? Well, what if your contact data, like who you're friends with, is sold to data brokers to give you a quote unquote better ads? This might not be something that you actually want. And it could be the case that unionizing workers are actually being cracked down on because they are identified through who were talking to each other and setting up these meetings. In certain countries, for example, in Denmark, unionizing is maybe not such a sensitive thing to be doing, but in other countries it could be. At the end of the day, I'm hoping that now you're thinking, well, this is all my data. This is information about my behavior, when I'm online, what I'm doing, and who I talk to. So this is something that I want to protect. We want privacy, right? We want metadata privacy. So this is to say in this talk, because metadata privacy, right, and could mean more things than what I'm talking about, but in this talk specifically, I mean the confidentiality of transport layer metadata. So basically, what you can see through TCP headers, like where's the traffic heading, and what time is it, how big is it, and so on. Okay, so I'm not the first one to study this problem. There is already a sort of known solution space out there, and it's sort of being made clear how big the solution space is by this paper that came out in 2018 called The Anonymity Trilemma by Das et al. So they say strong anonymity, low bandwidth overhead, low latency, you can only choose two. So we would ideally like all three of them, but they actually show an impossibility results of achieving all of it. So that means that the viable solution space is actually constrained by this proof that they have. So I want to draw that for you. And now I will say strong privacy instead of strong anonymity, but that will mean the same thing, just to be consistent with the rest of the language that I'm using. Right, so here you have the dimensions of strong privacy, low bandwidth, and low latency. And when we look at the existing solutions, we have something called dining cryptographer nets, DC nets. That's when this problem was first formulated in 1981, and then there is a bunch of implementations and improvements on this. If you don't know what a DC network is, don't worry, because I will show you an example. Again, I'm gonna show kind of a version that's adopted for instant messaging here, where we have a server that will be forwarding everything. So we have Alice, Bob, Charlie, and Dorothy who wants to send messages, and it's made in such a way that you will have different rounds. These will be predetermined in advance or be on some sort of public schedule. So basically Mallory will know when the round is, and that's not a problem. So when a round happens, everyone has to say something. So in this case, everyone sends an actual message, and Bob doesn't have anything to send, but he still has to participate. So he sends this dummy message, which is just, these will all be encrypted so they look the same, so it's not a problem. But he needs to participate even though he has nothing to say. And then this goes on for however rounds this protocol is defined as, right? And at some point, no one might have anything to say, but everyone needs to continue to communicate, because if you stop communicating, right, you're sort of leaking that I actually have nothing more secret to say. And if Bob then were to leave, there is only 3 people in this anonymity set of who could have sent something. So it's important that everyone stays online and follows the protocol until it's over. And if this is instant messaging, you might want to continue running this for forever. So that's DC nets in a nutshell. Then most of the practical solutions that we see, they're designed to be more performant. They will, of course, try to favor both low bandwidth and low latency, but this means that they have to sacrifice strong privacy, right? So for example, the onion router Tor, which is the solution in this space I think that most people will have heard of, because that is one of the few practically deployed solutions out there. But Tor actually doesn't manage to get strong privacy. So there's attacks against Tor because it's not designed to protect against a global adversary, but rather a local one that's slightly weaker. So not the malicious Mallory we are considering. And then there's something called mixed nets. These are also early work from 1988. And I'll also show you a little bit conceptually how they work. So we have Alice and Bob wanting to communicate, and then there is a bunch of other computers on the way between them that form this mixed net. And when Alice wants to send her message, it actually gets forwarded on some path through the network before it reaches Bob. And at each node, the message is also typically delayed, so that it doesn't just get immediately forwarded so that you could see where it is. So it means that you might have a message going to the first node and being delayed, and more messages will come in here, and then at some specific point all of them gets forwarded. And then they can also add dummy messages in there, and it just creates this extra traffic to hide in. So this is the sort of gist of how mixed nets work. An example there is the Loopix anonymity system from 2017, and the most sort of practical version of that is that there is an implementation called NUM, which is kind of a Tor competitor, if you will. It's based on Loopix. It's not exactly Loopix, but it's similar. So it has actually a stronger privacy guarantee than Tor. This is what the known solution space looks like. So why don't we have more deployments with metadata privacy yet? I mean, you might have heard of Tor, and maybe you've heard of NUM, but those are really the only 2 solutions out there. So let me give you an overview of what the challenges are here. So first of all, Tor, it didn't reach the strong privacy, right? So it can actually be de-anonymized, and there are multiple attacks against it. So it only protects against a passive local adversary, and we've talked about malicious Mallory here, who's a global adversary. So she can actually have effective attacks against Tor, where she just de-anonymizes and find out who you're talking to. One example is what's called watermark attacks, and that's when she's actually even an active adversary and manages to insert traffic patterns. For example, let's say that she has one of the, in Tor, right, you're routed on a random path of other participants. So let's say that Mallory actually is one of those forwarding nodes. What she could do is she could delay the traffic, because, I mean, she is one of the forwarders, right? So she just delays the traffic. Maybe first she starts with, maybe it's 10 milliseconds and then 20 and then 30 and 40, 50 and so on and so forth, right? Or some other nice pattern, that pattern will actually be retained all the way until the final node. And then she can just look for her so-called watermark to see where the traffic went. So, and there's a bunch of other attacks. So this is problematic because Tor is not as strong as we would like it to be, even though that is the thing that exists in the wild, if you will. Then these DC nets that we looked at, they are very resource exhaustive because it requires users to constantly be online to participate in these rounds. So imagine that you're running this on your phone, for example. This is not really great for your battery. And at this point in time, your phone might also be saying, hey, there's this app running in the background, there's this app draining battery in the background. You're not using it because, you are not communicating. Do you want to turn it off? And this would actually be really bad if everyone who was not using it turned it off, because then the anonymity set shrinks, which means by opting out, you are affecting the privacy guarantee of everyone else in the network by making, or in the protocol, by making it smaller. So it's not really feasible to be running these on rounds all the time, unless it's maybe at a very low frequency. Imagine maybe once per day, but then it also becomes less useful. Then there are also mixed nets, right? And they are slow in practice in comparison to Tor. So I look specifically at Loopix. And if you look at the latency, it's in the order of seconds compared to Tor, where it's milliseconds. So for a user, this might just be too slow. They can't actually use it, even though it would give them good privacy. Okay, so what about finding a new trade-off? So here we made some observations. And first of all is that all these traditional defenses, they're applied on the transport layer. But the network traffic is just a symptom. The actual problem, right, the thing that we're trying to protect is user behavior. And that means that, when the user is doing something on their computer, like I want to send an email, I want to send a message, I want to go to a website, I want to do whatever. That is what creates the network traffic. It's the user's action. So user interacting with a program is what causes network traffic to happen. But usually the protocol starts with looking at the network traffic and not at what is the user actually doing. So we thought, what if we could track and prevent leakage on the application layer rather than looking just at the network, where it's sort of, in some sense, it's already happened, right? So we were suggesting a hybrid model. I will tell you why it's hybrid. And we said it's a very ambitious goal of the existing literature to try to hide all the traffic. And that's what sort of puts us in this trilemma space, right? Because we're trying to do this for everything. What if we could hide only some traffic? So we basically proposed that we could use this other traffic as a vessel and tunnel traffic. So I would have a tunnel, for example, it could be the signal protocol, which is typically used in these instant messaging protocols. This is actually what we do in our implementation. It could be an email protocol like SMTP or web traffic, HTTPS. And then you could put your secret messages inside there to basically make it look like this is only some traffic that I'm not trying to hide. And then inside of it, you're hiding something. So the tunnel itself will be observable and those secret messages would not. And how we actually do it is, so you have some tunnel, you have the secret messages, and then we basically chop up these secret messages and put them as a trailer on the existing observable message. So we sort of added some padding over there and piggyback our message. And this is actually unintuitive because if you know your security foundations, you know of Seltzer and Schroeder's security design principles, and this actually violates what's called the least common mechanism. The least common mechanism says that if you have something of high security or high secrecy, you should not be mixing it with something of low and sort of public context. If you put these together, you're at risk of accidentally leaking something. So what we have to do then is we need to prove that we are not accidentally leaking something. Otherwise, this is just not a viable solution. So what we do is we prove there is no leak from the secret program to the tunnel. So right, that sounds easy. I'm gonna elaborate a little bit on how do you actually do that. So first of all, you wanna show that your program state does not leak, because you might require a protocol update for this not to happen. So in our case, in the paper that I will show you later, we started in the Signal messaging protocol. So this is the crypto protocol behind the Signal, WhatsApp, for example, and Facebook Messenger. But it turns out that if you just take Signal and just put it as padding here and try to piggyback the original protocol, the protocol itself carries a state that leaks information. For example, the attacker can request keys through there if they're active. And then they can start counting how many keys exist in the key distribution center and so on and so forth. And so actually it turns out that if we want to piggyback in a secure way, we have to sometimes change this protocol. So we first then prove that there is nothing leaky from the protocol. And then we also need to prove that the network traces, so whatever communication is observable to Mallory on the network, that they are indistinguishable. Basically that she cannot tell if there are secret messages or not inside of this tunnel. I will dig a little bit more into detail on this so you understand what I mean. So indistinguishable traces. For what we first do is we compare two network traces of the same length. So these are the two that we want to show that they are the same. So they are any two traces of the same length where these observable messages are the same. And then we need to show that the encryption looks the same. And that is not right. It doesn't always encrypt to the same value because then it would actually not be secure. But we show that secret messages and dummy messages are random in the same way, if you will, similar to how it works in TLS. You don't always encrypt the same plain text to the same ciphertext because then you could see that you're just sending the same message over and over, right? So you want to say that they sort of come from the same probability distribution. And then this is what you're basically showing, right? That if you chop up a message, a secret message with some content and piggyback that, that thing should look almost the same as if you take a dummy message, no content or zero padding, and chop that up. This should look the same to Mallory as long as these other messages are actually the same ones because she can see what these are. They will be encrypted as well, but she can see sort of how many they are, right? And maybe the length to some extent. And then we also need to fix the length of padding. So the length of the secret part is public knowledge. So the size of this red part here actually needs to be something that Mallory can see. Well, actually she can see that size and still not learn anything because of how we show this indistinguishability. So this is how you show that the traces are indistinguishable. And the main insight, if you can remember something from today, I want it to be this slide because this is something which I think is our sort of main contribution to the area so far. And that's actually what to prove. So we can express metadata privacy as the property non-interference. You might have heard of non-interference before, and if you haven't, don't worry, I will again explain it. So basically, we think of having some unobservable communication. In this case, this is where I want to put my secret messages, right? So there's this flow from some input of unobservable communication from Alice, right? And going to the output, which is going to be Bob. And then it travels at some point here over the network. So this is something that's usually referred to as high. That's what the H is, high context. So this is private stuff, secret stuff. And then we have some public channel, in this case, the network that Mallory can observe. We usually call this context low, and it flows over the network, right? So when we want to prove non-interference, the flows that are okay is that the public input can flow into the high context. So anything that's observable on the network can affect the secret messages because Mallory can learn everything about this anyway, so it doesn't matter. But what's not okay is that we can't have any flows going from the high context into the low. So basically, the secret messages should not just flow out on the network and be visible to Mallory. This is the formal property that we want to prove. And what it means for privacy is basically that the input to our program over here, the unobservable communication, what Alice does, right? The user behavior doesn't leak to the network, which is a public channel. So Alice's behavior, which we see over here, doesn't leak on the public channel. So that we prove by non-interference. And essentially what we're doing, right, is tunneling, and here's what it will look like for Mallory. So we have this unobservable communication and the public channel, and so Alice will be wanting to talk to Bob. This is the secret chat she wants to have. So she wants to send a secret message to Bob that no one should observe. But the way of doing it is she actually sends a real message that is observable to Charlie, her friend, that she has no problem of Mallory knowing about. And because we have the centralized server and instant messaging, we're actually able to then piggyback the messages to the server and then wait for someone else to talk to Bob, where we can piggyback the messages to him. And this means that we break the direct channel, the direct connection, right, the link on the network between Alice and Bob. So to Mallory, what she will see is just Alice talks to Charlie. And at some point, you might see that some other person like Dorothy talks to Bob, but she never sees any direct link between Alice and Bob. And then we formalize this with non-interference. So to conclude, metadata leaks on the transport layer unless we use some dedicated protocols. So encryption alone is not enough to stop this. We do need encryption, and then we need this other protocol to be protecting the metadata. And this is especially bad for us if Mallory is a strong attacker, because then she might be exploring the entire network and observing it. So then we need the strongest protocol that we saw in the anonymity trilemma. So the existing solutions tend to focus on symptoms, so network traffic. And so what we see is an opportunity to design application-aware protocols that focus on what is the user doing and how is the information flowing in the system, rather than trying to go for a one-size-fits-all solution. And we think that this is actually opening up the design space to think of more performant protocols. So maybe we can sort of find a new trilemma, or see if the trilemma still holds within our version of the problem, right? And if we tweak the threat model, we can find new trade-offs that weren't open before. In this case, we're focusing on hiding some of the traffic instead of all, to see if maybe this can give us solutions that are actually deployable and giving the privacy that we wanted, hopefully. You know? And we also show that metadata confidentiality can be viewed as an information flow problem. This is where we're borrowing this property of non-interference. So you can get privacy guarantees from proving non-interference. And I also want to give a shout out to my co-authors on this paper, Elena Panin and Aslan Ascaro. So if you want to read this paper and see more how we're doing it and how we're redesigning the Signal protocol, this paper is available free online. And currently we're still working on more solutions in this space. Of course, designing more protocols, focusing on the being more performant, but still retaining the strong privacy, and also looking into programmatic or sort of programmable defenses. So basically what we're doing now is designing programming languages so we can write programs, so application aware, that get some provable guarantees of unobservability. Yeah, so if you're interested in that, please keep in touch and check out our latest work. So thank you very much for listening.